I will be a host today, together with Dr. Tankiso and Rudimi Emmanuel. So today's topic is titled Advancing Urban Building Energy Modeling, a hands-on approach to addressing data challenges for sustainable and resilient cities. I would like to call on Dr. Tankiso to give the mission statement for young practitioners in construction. Dr. Tankiso?
Good evening. Good evening.
Oh,
Good
yes.
evening. Can you hear me?
Yes, I can hear you loud and clear.
Okay, thank you. Good evening, everyone. I'm here to present the mission statement, and it reads as follows: empowering young practitioners through strategic partnership and organizing programs in the built environment. Thank you.
Thank you, Dr. Tankiso. I would also like to call on Rudimi Emmanuel to give the citation of today's speaker.
Good evening, everyone. Thank you, Mr. Moderator, for this privilege to read the speaker citation. And I will go straight to reading the speaker citation. Our guest speaker today is Engineer Arumi Anand. He's a member of the India Institute of Technology, Bombay, Mumbai, India. He's also an expertise in remote sensing, GIS, energy stimulation tools. I would like to share the PPA of the citation.
Okay. Thank you, Emmanuel. You can share.
Okay. I don't know if we can see it.
It is visible. Thank you.
Okay. The speaker is Engineer Aruni Anand, a member of the India Institute of Technology, Bombay, Mumbai, India. He's also an expertise in remote sensing, GIS, energy stimulation tools. Thank you.
Thank you, Emmanuel. Before we hand over to our speaker, just a quick housekeeping. I kindly request all the attendees who have joined this webinar to please keep your microphones on mute while our speaker does his presentation. After the presentation, there will be a Q&A session. So without further ado, Mr. Aruni Anand, I am handing over to you. The floor is all yours. Thank you.
Hello, everyone. I hope I am audible to you all.
Yes, you are audible. Thank you, Harinam.
Okay, very nice. Thank you, organizers and the host, and thank you, Emmanuel, for the introduction. So today I'll be talking about something which is relatively new in the building construction field, and it's called urban building energy modeling. So before I share my slides and before I go on to a hands-on, demonstration of how we do that, uh, I would just like to, check whether I'm able to share my screen or not. Just give me one moment. All right. So are you able to see my screen?
We are able to see the screen. Thank you.
Great, great, thanks. So, the topic for today's discussion is advancing urban building energy modeling, a hands-on approach to addressing data challenges for sustainable and resilient cities. I am Arun Manan. I am a PhD research scholar at the Indian Institute of Technology, Bombay, and I'm working with two professors, Ishwar Rajasekharan and Chirag Dev, and both of them are associated with IIT Bombay. Apart from that, Chirag Dev is also associated with the University of Sydney at New South Wales, Australia. So I'll just start with a quick introduction. Why this topic is relevant? Why urban building energy modeling is coming into picture from last 1 decade or maybe 1.5 decades, so 10 to 15 years. So what is happening is urban areas are consuming over 70% of the global energies. And with urban area, don't specifically mean cities. It can also be small towns. And depending upon the region or the country where you are located, the definition can vary. But for example, in India, there is a constraint on population and population density, and that's how the urban areas are defined. So uh, apart from just the urban areas and the share of cities, inside the cities, buildings have 34% share in global energy consumption. So we can see we have a good share of energy consumption from transport and residential buildings, non-residential buildings, and this data is valid throughout the world. Okay, and even for the Indian cities, 37% of the total and annual primary energy consumption is from buildings. And this rising demand for air conditioning, which is due to climate change and rapid urbanization, these things are pushing up the peak in power demand. For example, because I'm located in India and I've been observing and reading about India a lot, and uh, some reports are saying that India is set to more than double its building space over the next 2 decades, with 70% of new construction happening in urban areas. So, what will happen is basically this percentage of energy demand is going to increase. And we have the sustainable development goals where we talk about ensuring access to affordable, reliable, sustainable, and modern energy for all, and then making cities resilient and sustainable. It is very important to tackle energy consumption, and the only way forward is sustainable and energy efficient buildings. Given we have climate change, urbanization, and other phenomena like urban heat island, if you have heard of. So why we are focusing on buildings? Because there is just one simple explanation. When there will be more buildings, there will be more energy demand. But at the same time, as I mentioned, there are factors such as climate and urban form, then the design of the building, the construction type, and lots of things which affect energy demand. And there are plenty of literature, plenty of research papers to show everything. Currently, the focus is on cooling energy demand because of the global warming, and for a country like India and most of the warm countries, this is a major concern. There is a very famous statement by a philosopher and an analyst, who said that you can't manage something that you can't measure. So, with that, this technology called urban building energy demand comes into picture. So basically, what was happening is, uh, for a given building, for one building or two buildings, there were building energy models, and these were utilized extensively. So these are a coupled model with BIMs, building information models, which were used for simulating energy demand and even predicting it for various scenarios. But what is happening is due to the requirement of policies and reforms at city level, because it's very difficult to implement policies for individual buildings. So it is necessary to keep policies and reforms at city level. So at larger scale, this urban building energy modeling is the key. So it ranges from a neighborhood level to community level up to city and district level. So moving from one building, we are moving to multiple buildings, even a city. The basic framework starts. The framework is very simple. Uh, the model takes into three to four types of data. The climate file of the region where the city or the selected area where you want to work upon is situated. Then the characteristics of the building. We'll talk more about this because this is our topic today. And then occupancy data. Like how many people are living in the building and what appliances they are using, what are the schedules and everything. So then these data sets, there can be a demand modeling interface, UI, or there can be, a collection of code scripts where we'll enter all these data sets. There are predefined thermodynamical equations. Those will be part of the UBM simulation, and we'll get the result in terms of many things. For example, energy performance index and energy use intensity, then future energy demand and renewable energy ratio and whatnot. So currently, people are also working on getting the renewable energy potential through this technology. So, for example, putting solar voltaic cells on photovoltaic cells on rooftop is something new in our country. Okay, so basically what happens is the most critical part in UVM is the data part. I mean, when we go to the previous slide, I mentioned about climate data, building data, and occupancy data. So the data part is the most critical part where everyone is struggling. Okay, so the entire database for UBM is very comprehensive. So it has a physical component which has building orientation, height, uses information, for example, whether the building is residential or a commercial or office or a retail, or it can be a shop, it can be anything. Then energy reference area, surface area of facades. So apart from the roof area, there is like the volume to surface area to volume ratio. Then geolocation, what is the location of the building, elevation of the building, and U value of wall, windows, roofs, etc., which is basically dependent a lot on the construction material, temperature of the internal surfaces and external surfaces. And there are some more, but I have tried to compile these things in one box, and this is the physical component. So apart from this, the climate component involves air temperature, humidity, solar radiation, wind speed, precipitation, indoor air temperature, wind speed, air tightness. These all go into UVM database. And apart from that, we have occupants and appliance related data, as I mentioned, which has the number of occupants and their actions, then set point changes, then what appliances they are using. For example, air condition, hot and cold water consumption, what is the efficiency of the appliances that they're using. All of these data sets, we have multiple methods to collect the data for all the buildings. For example, if you go to a field and there are like 1000 buildings on the field, you can collect collect substantial amount of data. But if the number of buildings are more, for example, if there are 5,000, 6,000 buildings, then that will be a tedious and challenging task. So we have some solutions in form of satellite images, flying a drone. So some of the climatic and physical component can be measured by uh, drone images because they are very high resolution, maybe in the range of even zero point 0.2 meters, 20 to 25 centimeters spatially. And then we have satellite images which is under 1 meter. uh, Again, these have some potentials and some limitations as well. So as I said, all of these data sets go into UI. The simulations are performed and we get energy demand profile and etc. etc. So the concern here is about the collecting the data, and that is the main discussion of main topic of the discussion today. So what I have done is, to make things simple, I have gone through each and every literature and research papers which mention about the potential of satellite images and drones. UAV is basically drone unmanned aerial vehicle, to collect the data for urban building energy modeling. So basically, the data sets were collected not for UBEM but for some other purpose. But I have compiled them in a way that, for a person who is starting to learn UBIM or starting to collect data for their project, they can refer to this, and they can download the satellite image. They can fly a drone and get some data for this. So this makes things simpler. But here there is one problem. For example, remote sensing and GIS, including satellite image and UAV, they do not seem to offer much for the occupants and appliance related UBM inputs, because these are largely dependent upon human behavior. For example, for how many hours of day someone is switching on his or her air condition, or for how many hours somebody is using a particular appliance, is very much dependent upon one specific behavior, right? So so there is a catch, and this is it. Yeah. So about the data part, uh, for many cities around the world, the building databases are available. I mean, either the government or a third party agency provides the building data, either freely, or you have to pay some money, but you'll get most of the data for buildings. But for many cities, it is not there. For example, in my country, India, the databases are not available at most for most of the cities, and we have to create the database ourselves. Apart from that, even high resolution satellite data under 1 meter is very difficult to acquire. Either it is very costly, or it is restricted by policies, or due to security reasons. And creating a 3D model requires extensive data acquisition. For example, putting a LiDAR station, or flying a UAV with LiDAR or thermal sensors, these things are very challenging due to security reasons. So these are the concerns. I am currently working on collecting the data and finding out sources which from where I can get open source building databases. So I have some of the key observations with which I work. So what happens is, most of the UBEM approaches, so there are multiple tools and softwares and platforms available. Some of the platforms are even open source. So one of the open source software I'll demonstrate here just after the slides. So most of the approaches are based on available databases, either to the physical or the climatic conditions of the specific regions. But as I mentioned, structured database is not available. So even if you get the database for buildings in many cities, you still have to create a database in a way that it can be used directly in UBIM software. Right. So there are some work being done around the world, which are focused on finding the alternate approaches based on clustering and modeling of building variables or urban variables. So basically, what we do is, we find variables. For example, the input database that I explained about in UBIM. These are the input which we put in the software, but these are the variables that influence energy demand as well, right? So people are using clustering or machine learning and modeling of these variables, and specifying buildings according to their energy demand and putting them in classes. So people are exploring these things, and I am also currently, my research is more or less based on this topic only. So what happens is, I'll just show you one example of the input data issue. For example, this image shows this Google satellite image. So shows you a part of Mumbai, a small area of Mumbai, where there are like 20-30 buildings. And the first image, which is the image of actual building, these have like I have digitized the green rooftops in green polygons. So these are the rooftops of the building. So we need this in UBEM, urban building and energy modeling, but we need the footprints. So we just have to put an algorithm and we can shift the rooftop to its base depending upon the relief distance, I mean the oblique angle of the photograph. However, the two other images that are being shown here are of open source. Open source means it's freely available on internet. You can download Google Building Footprint for many cities around the world and OpenStreetMap footprint. So these are the examples of Google Building Footprints and OpenStreetMap OS. We'll call it OSM from now onwards. Google Buildings and OSM footprints for the same area, and you can see that the buildings are either absent or two three buildings are getting merged into one, or either the geometry is wrong, right? So this is a critical issue because when we go to the modeling, the results will be substantially varying, So what happens is, okay, apart from the footprint, I must mention that these data sets, these open source free data sets, such as Google Buildings and OSM Heights, and many of them provide the data for height and number of floors as well. But as you can see, the first one has the name of the building and the actual data that I have collected from the field in terms of floors above ground, floors below ground, height above ground, and height below ground. So this data set, you can take a minute to just see the difference between the two data sets. So basically, the data that I have collected, it has number of floors varying from 5, 8, 13, 19, 17, 21. And in the free data set, the number of floors remain constant. It is 1. So when I model this in urban building energy modeling, the result will be substantially varying. So this is just one example of the input data issue. So this is the result of the model which I ran here in, just give me 1 minute. Yeah. So this table shows the result of energy demand in form of matrix. So when we compare actual geometry to the OSM data and Google Building, the OSM data is giving the energy demand as 0.73 times the actual energy demand, which is just the 70% of the actual energy demand, and the Google Building is giving 80% of the actual energy demand. So if we are going to predict the energy demand for a future scenario, again the numbers will be can be either reduced or increased. So that is the issue with the current data set that we are having. And similarly for climate data, I'll just show you. I'll quickly let you go through the climate data variable. So for example, as I showed as I showed 3 data sets for building, we have multiple data sets for climate as well. So one of that is CPCB weather station, which is the most reliable one because it is ground-based, sensor-based observation. Then we have ISHRE EPW weather file. It is a climate file in EPW format, energy plus weather format, which is provided by a society called ISHRE. And then there's ERA5 climate data, which is a geospatial form of data, and it's a reanalysis data. So what we do is here is okay, yeah. So I'll just show you the a quick image of everything. So for example, IIT Bombay campus, the the blue colored circle and the crossed polygon which you can see in the left Google image is the campus area of IIT Bombay, and we have one sensor installed there which gives us the weather data in EPW format. Sorry, in Excel format, and then we have the EPW format of data in for the same area, and we have ERA5 reanalysis data for entire city, and we have like 3 to 4 tiles covering the entire area. And so what happens is, for example, in this demonstration, I have selected some of the buildings in the area, and I have collected the data for geometry, envelope, properties, usage, everything. and use 3 types of climate data, right, to find out the energy demand and energy use intensity. So basically, energy use intensity is nothing but energy demand per square meter of area and per year. So it can be square meter or whatever unit is relevant to your region, but it is dependent upon the number of floors and you know the area surface area of the floor. So this is a distribution of energy demand, and but that is not the concern. The thing is, some of the geospatial data, I mean the era data, is giving very good result for for the in place of sensor data. So if we consider the ground-based sensor as the correct data, the energy demand results from the ground-based sensor, and the energy demand results from the geospatial data is very good. I mean they are aligning. The correlation coefficient is very good, but for the ISHRE data, I mean the EPW format data, the error margin is high, and unfortunately that data is widely used. I mean ERA 5 and the CPCB data is not used widely, but the ISHRE data, the DPW format data has been uh, used from last 3 decades or 4 decades continuously. So that's the situation, and uh, just some results for differently for residential buildings and non-residential buildings, and I mean all buildings. So we have some takeaways from here. The first one is very basic, and so basically the discrepancies in building data and climate data lead to substantial differences. Then, in place of if you don't have ground-based sensor present, you can use geospatial platforms which can give you good quality of data. I mean, obviously, data has to be validated. So the first step is validation, but a validation and integration of ground truth and high resolution data set is desired. So with that, what uh, what are some other concerns which are important, like for example how the climatic conditions vary inside a city. So for example, there can be areas where there are trees and the built environment is very green, but there can be areas where the buildings are very clustered. I mean, there is a high density of building. Then impacts of urban heat island and climatic variation. For example, uh, urban heat island is a phenomena where where the temperature of surrounding areas is a bit less than the urban area from the core area. So all these things affect, and so basically what happens is you have the climate file, you can model it into the software, you can get the energy demand result, but getting the accurate climate file, getting the accurate building file, building database is the challenge. So this is just a demonstration of how we create models in city in any UBIM software. So this is from a particular software which is called City Energy Analyst. I'll be showing you some of the snippets from the software. So this is for 2 areas in Mumbai. Mumbai is one of the major city in India. The first one is obviously the IIT Bombay campus, the top one, where the footprints have been created using satellite images, geospatial images, and some field data, and then the height is modeled. Similarly, the second image, the lower images for some other area in Mumbai. So what happens is there are like for the 2 areas the variation, there is some variation in cooling energy use intensity, and with height the energy demand varies. I mean, if you try to increase, if the height of the building is more, I mean the number of floors is uh, high, then the the EUI decreases basically. So that is particularly because the lower floors are less exposed to the solar radiation and heat. So that is why it keeps on decreasing. So this is one of the observation. So I think because we have limited time, I should move to the demonstration of the software as well. So I'll just quickly go through the concerns. So this is something to be explored if any one of you want to explore this UBIM part. You should I mean these are some of the focus areas. The first one is that sensitivity of the factors, like what are the integrated factors in urban areas which can affect the energy demand apart from the input variables. And then what is the efficiency, I mean how can we move to the optimum efficiency at an urban scale? And for multiple cities, these should be constant. So the way forward is either the built environment planning or retrofits and solution. So retrofit and solution is a bit tricky because a policy level retrofit is difficult because it depends upon the owners and the occupants and lots of things. So built environment planning is something which can be done for at least future cities, I mean future urban form. And what is important here is the identification of features which affect urban energy demand. And so I've listed some of the features which are not only at building level but at a neighborhood or urban level. These things affect the energy demand. I mean specifically the cooling and heating energy demand. So height, compactness, and the construction material, the airflow, the passage, so it requires a computational fluid dynamic equation. Then surface area of the buildings, orientation of the buildings with respect to sun, then shape of the building and shading. Shading can be due to the surrounding buildings or even the vegetation or trees planted near the buildings. For example, this is one of a this is a typical urban settlement. This is from Navi Mumbai. It's a city just beside Mumbai, and it's a metro city in India. And this is a snippet of 1,200 buildings, in which I think more than 90% is residential. Some of the buildings are mixed use, for example, residential plus retail or residential plus office or something. So you can see a mix of all kinds of building here. I mean, high rise, low rise, high density settlement. The top right corner, you can see the settlement, which is, informal high density settlement. Okay. Uh, so the problem here is if someone wants to work on, particularly on, one or other region, what happens is the definition of the urban area varies. I mean, the urban area, or what you can say is the urban morphology varies. For example, the the left image is a low density region, right? It's an open area, so we can find the total footprint area divided by total area, and we can just say that it's a relatively open area and buildings are sparsely located. And the right one, which is a mixed density region, here the problem is that when you will divide the total footprint area by total area, again you'll get the same value probably, but here there are three different kinds of urban forms situated. I mean, the first one is highly dense packed buildings all stacked together. The second one is relatively spaced, and the last one is partially situated buildings. So these definitions, these formulas do not work here at all. So I am currently working on finding the solution for these things. But for example, the image that I showed you just now, it has high density low rise, high density mid rise, mid density low rise, all kinds of urban forms situated, and that is my area of concern. So I'm trying to figure out a possible approach where I don't have to collect data for each and every building, although I have collected for this area because my result has to be validated at the end. So I'm trying to find approach. I am basically following a clustering and machine learning approach to find the optimum solution. Just an example of how the results look like. I mean, you can just take a moment to just look at the image. And EUI is energy use intensity, which I explained previously. And this image has been created in GIS, in one of the GIS software, Quantum GIS. And the results are from software, open source software named City Energy Analyst. So we'll be moving to a demonstration of that software now. Okay, some references. So let's go to the software. Yeah. Okay. So this is a software, this is a model, City Energy Analyst. This has been developed in ETH Zurich in their architecture department. So the front page, if you can download this software anytime, it's freely available on internet. and you can use it for energy demand simulation at urban scale, even at one building, even for one building, for a neighborhood level, like 15 to 20 buildings, or even for the entire city. Just that, I mean, the computation time will be high. So the front screen of the software looks like this. Either you can create a new project, or you can open a previously started project here. In this case, I'll be starting a new project. Okay. Okay. So it can be the name of the project. Name can be anything. For example, I can just name it demo_1. And this is the location. This is the path of the project. So I am currently saving my project here in my PC. So when you do that, yeah. So when you do that, there's an option to create scenario. So basically what happens is, uh, let's say for one given urban area, for one particular city, you have three types of weather data: one for present, one for 2030, and one for 2040. And the weather data is a projected weather data using climate models and everything. And you want to compare how much is the energy demand from now to future. You can create three scenarios here only, and you can compare all the results of all the scenario here. I mean, in one particular project. So there is an option to create multiple scenarios here. I mean, you can create as many scenarios as you want. So I'll just create one scenario here to demonstrate. So clicking on scenario gives me this dialog box, and let's say I name this scenario something demo scenario _1. Then this is the database contained within the CEA. So the software has some database created within itself. The database means doesn't means the building input database that I have been talking about from last 30 minutes. I mean, this database means uh, the next step. I mean, what are the practices, construction practices in a particular city? So it has. I'll show you in the later steps. So for example, I can click SG, or I can click anything here. We have an option to change everything in later steps. So for the input data, either we can create the data here only, or we can import input files. So if you have like building database and climate files ready with you, somebody has provided you, or you have collected data and created input files. So for example, building databases can be created in shapefile format. Shapefile format, basically, we use shapefile format for GIS datasets, and those are like super simple to use. If you're familiar with GIS, you'll be knowing what I'm talking about. So there's an option to generate new files using this tool only, or you can import input files. But for this demonstration, I'll be generating the input files here. So apart from the buildings, we need some data for surroundings, for example, street, terrain. For weather, it can create itself, but we can use a weather file which we have, like for a particular area. Now, if we have the lat long of the study area, you can just put the latitude and longitude, and you can go there. But in this case, I don't have, for example. So I'll just zoom in here, and I'll find out where my. So yeah, so this map which is displaying here, you can read it's OpenStreetMap. So this is from the OpenStreetMaps, which I have shown you previously. So 1 second, I'll just zoom here. Yeah, this is my institute campus. Sorry for uh, my bad throat. This is due to the climate. Yeah, okay. So as you can see, there are some buildings which are already created here. So for the campus of IIT Bombay, most of the buildings are actually more or less correct in terms of geometry and position. So OpenStreetMap people have done well here, but it's not true for the entire city or for any part of the world. So you should be very careful, and you should once check with Google Earth image or any other satellite image whether the footprints are displaying correctly or not. So you can just draw a a draw area over here. For example, I'll be just drawing a small area here because then I can move forward. Otherwise, in the given time, I will not be able to move forward if I select large number of buildings. Double click here, and for example, this area has been I have demarcated, and this polygon I have created. When I click on create, it will try to create a scenario. It may not, but it will try to create. Hopefully, it gets created. So let's wait for a minute. Yeah. So it's so the scenario is created. Now this screen shows you the comprehensive UI where you can enter the input variables. I mean, uh, as you can see, these are the name of the buildings. If I click on one particular building, that building is getting highlighted in yellow. Okay. So I created the boundary here, but 5 buildings outside the boundary has also been uh, highlighted, and these are displayed here in you can see zone, typology, architecture. All these are inputs. The these 5 buildings are highlighted here in surroundings. So see, because surrounding buildings also affect the energy demand of the of any particular focus building due to shadow, wind obstruction, and many things. So first thing is we need to enter the floors, number of height, I mean number of floors above ground, below ground, height of the floor. So when you hover on the column name, it shows you the full description of the the column, and you can enter accordingly. So for this case, we are going to let it be, because it's just a demonstration, and even I do not remember the number of floors exactly for all these buildings. So this is one input. Then the next input is typology, where we have to enter the year of construction. Yeah, year of construction. Then yeah, this is the database that I have been talking about. This is construction standard. So for example, we selected SG. So the standard one, you can see the definition here. Concrete and masonry is essential reduced conditioned area. We have commercial. We have like different options here. Standard 1, standard 2, standard 3, 4, and 5. And we have all these standards mentioned here in the left panel called database editor. Okay. And don't worry, we can go back to that screen very soon. So this is a particular kind of database which is already stored here. We can modify this database as well, but we'll not go into that. For now, we'll keep we'll keep it simple. So yeah, now this is first use type of the building. So there are multiple options here: multi-residential, single residential, hotel, office, retail, food store, and industrial, university, school, and whatnot. So this is the first use, the major use. For example, this is multi-residential. The number here is 1. If it's a mixed use building, you can put it as 0.8 or 0.7 depending upon what percentage of the building is being used in what form. So for example, it can be 0.8, and the second use you can select as an office, and it can be 0.2. Similarly, we move on to third use and so on. So these two inputs, surrounding input, tree input, everything you can enter. So what happens is the architecture, internal load, indoor comfort, and up to supply system, even the schedule and tree, all these we have to create in the software itself. So once you're done with zone and typology thing, you can go to data management, archetypes mapper, and the software will create these, but obviously you'll have to change it according to your data. I mean, according to your field data or whatever data you have for the buildings. So I've just tried running a simple archetype mapper. It should not take much time. It should be taking maybe less than a minute. Yeah, so it's completed. So now if I go back to my input editor, it will have something created here already. For example, number of floors with an open envelope from the ground. You can edit these. I mean, these are editable. Okay, so for example, fraction of a ground floor around gross floor area air conditioned, then below ground, and net gross floor area, window to wall ratio in each direction, type of construction, type of roof. We have option here to select type of roof. We have greenery, white paint over concrete as well now in the option. Type of shading, then we have type of wall. We have all these options to select. You can modify it, and you can also add more options by going here. I mean, the database editor, which I previously showed. Similarly, we have internal loads. I mean, occupancy density, how many meters square is designated to one person, and then peak sensible heat load of people. Similarly, we have like different options here. Indoor comfort. So when you're thinking about air condition or the cooling system, what is the set point temperature that you want to set, and what is the setback point temperature of the cooling system? Similarly, for the heating system, what is the lower bound of relative humidity? Everything you can provide for the each and every building. So you know you can edit either individually for each and every building, or you can select all and start editing for all the buildings together. Similarly, we have air condition system, supply system, everything. For surroundings, we have just two data, number of floors and height, because these two are the only important things. Uh, Obviously, the surface area of the buildings, it is taking by itself. Okay. So what happens here is, if we don't change anything, we can go to weather helper, and it has weather file for some part of the words already, in the software, but yeah. So I have an already built weather file for my city, which is in EPW format. So the model takes input in EPW format. EPW format is easily editable either in CSV Excel, which you can open in MS Excel, or in some software called Elementor. I forgot the name, but it's easily editable. So if you have a correct weather data, you can just edit the EPW file. So that's what I do and modify my climate data. So if I open it and run the script, so this is job ID 2. The first was archetype mapper. The second is weather helper, and it should be done very soon. Meanwhile, surroundings helper. I mean, the surroundings are already created, but let's say if you want to change the buffer, no, the perimeter, you want more buildings or anything. I don't know if it will create more building or not, but let's give it a try. If it doesn't, no issues. If I run script and create a surrounding helper, and then terrain. I mean, the terrain is just the a digital elevation model kind of thing. I mean, what is the topography of the area? So this we can also run, because it's a small area. The terrain will not differ. But if you're going for an entire city, a mountain, a hilly area or anything, then you should have a digital elevation model with you. Okay. Yeah. And then the streets helper and trees helpers. So basically, we don't have data for streets and tree currently, so we cannot enter it here. For example, for tree, it asks the path to shapefile. the same shapefile in which I mean the buildings are also created in shapefile format. Similarly, we can create trees in shapefile format and provide the name of the tree canopy height and density of the tree canopy and everything, and we can run it here, and then that also gets stored. But we don't have it here, so we'll not go into tree helper and street. So the first thing is building solar radiation. Another thing is I sorry to say, but when I run this solar radiation for each and every building and each and every wall and facade of the building, the solar radiation is calculated. The model follows a sun path diagram for any city which you have selected. So, for example, when I zoomed into the OpenStreetMap and selected Mumbai and went to my campus institute and selected the buildings, the model has a sun path diagram of that area in itself, and for all these buildings, it will, you know, it will calculate solar radiation. So if I run this, actually it will take much, I mean, too much time. I mean, so we have like 9-10 buildings, so it will still take like 10 to 15 minutes. So we'll not be doing that. So I have just run the script, but after running this, we have something called building schedule, and maybe this gets completed soon. So the schedule goes here. Let's show you. The schedule goes here. So for example, yeah. So this is building B1000, which is this building. For this building, we have occupancy. I mean, how much fraction of the occupancy is there for that particular house. So this is 12 a.m. and this is I think this is 1 a.m. and this is 12 a.m. at night. So probably the night times the ratio of the fraction is 1, and in the afternoon the model is assuming that people are going to their workplace, office, or school, universities, wherever. So it is giving a 0.25 or anything. So these all values are editable. You can edit these values, and you know you can populate the occupancy data. Again, you can select multiple buildings at a time or one building at a time, and you can work from. Then similarly, we have appliances, the same kind of fraction: lighting, servers, water, heating, cooling. Now, uh, for example, residential buildings, uh, cooling is cooling will not be much in the afternoon time, in the daytime, because obviously people will be gone to their workplaces. So this can we can click it off for the morning time, or the like maybe for you can click it as off for the daytime, and so on, like till 18, I mean till 6 p.m. in the evening. But again, I mean this can differ. This depends upon the actual data of the building. So that's why I was saying that field data is critical here, and remote sensing or GIS or anything is is not certain here. You have to get the data from the field. So here, if I click here, you can see the schedule maker is complete, but the radiation is still taking time. Um, so what we can do is, after this radiation is done, the only thing which is left is building energy demand. Occupancy is done. I mean, it's will not click now. So occupancy is nothing but the things which we are doing here. But once the radiation is done, we just have to click on building energy demand, and I'll show you how to calculate that. But as I am already over time, we can have the Q&A session now. And once the radiation is done, I'll show you the result. Okay. So apart from that, it also has life cycle analysis, energy potential network. I mean, lots of things are there, but this is the topic of today. I mean, building energy modeling. So this is the first step, the calculating the energy demand. And so yeah, so once it is done, I'll be showing you the result. So I am stopping the share, the screen share now, and coming back to me.
Thank you, Arunam. Thank you so much, Arunam Anand, for this wonderful presentation.
Yeah.
And I do hope you recover from your cold.
Oh yeah,
sorry
yeah,
about your
yeah.
cold.
Thank
Yeah.
you very much.
Yeah, no, thank you so much. Thank you for this lovely and very insightful presentation on urban building energy modeling, UBEM, by inputting building data and climate data to determine the energy use intensity, as well as identifying various types of urban settlements and calculating the EUI. Yeah, so this really is crucial for all professionals in this construction industry to continue to adapt and continue to improve on UBEM, and also, yeah, reduce the carbon emissions. Yeah. And we need to be in the forefront on sustainable technologies, as this affects our planet in the long run, on the decisions we make throughout, the project, the life cycle, and in terms of determining sustainable and resilient cities. Yeah, so thank you once again, Arunam.
I'll encourage everyone to have a look at, this is just one software that I have demonstrated. There are multiple
Yes.
softwares and scripts available on internet with the predefined physics, the thermodynamic equation, and everything is available online. So whoever is interested should go through it, and they can create their own model, their own software as well. And it will be wonderful, to be honest.
Oh, thank you so much. Thank you. Yeah, I hope everyone took note of that, and explore other softwares that are out there. So we are now in the Q&A session, and I would like to give the floor to the listeners, all the attendees who are listening to this impactful presentation. If there are any questions, you may kindly raise your hand, or you can type your questions on the chat. Are there any questions? You may kindly raise your hand if you have any questions. Yeah, it's clear that you gave a very wonderful presentation. There aren't any questions at the moment. I'm
It's
also
very
just
simple.
checking at the chat.
So I'll
Yes.
just show you the screen, because that thing is done. I mean, the job is done there. So I'll just show you.
Yes. Yes, please. Oh, yes. There is a hand raised by Fortune. Is it okay if
Yeah, sure.
can ask Fortune? Yeah, Fortune, you may give your question. Thank you.
Yeah. Thank you so much, the presenter, for this very enlightening presentation. And I want to ask, this software that you've just shown us, can we easily just go online to download it, or we'll need to subscribe for it?
No. You don't have to subscribe for it. I mean, you can just search City Energy Analyst. It will take you to the website, and you can. It's just a small box where you have to put your email ID, and it will be downloaded automatically in your PC, and you can just click on the installer, and it will be installed in your PC. So, and once it is installed, it will open this. Once it is installed, it will open only I mean the screen that I showed you the first. create new project. That is the first screen. There is no other issue with that. In fact, most of the UBIM open source freely available UBIM tools softwares are like that only. You don't have to subscribe. Yeah.
Okay, thank you so much for that.
So
Thank you, Fortune.
I'll just show you the So once it was done, this is the last step, building energy demand, and this will take maybe 1 minute. It will not take much. And so for example, I'd like to mention some things. For example, all the codes, all the scripts of this software. So open source means not just the software. In fact, the codes are also available. So you can, if someone is familiar with Python and a little bit of JavaScript and everything, they can use Google Earth Engine and this particular software, City Energy Analyst, and you can play along. You can play with the code. You can do whatever you want. So in fact, for my work, I'm not even using this UI because working with codes make it easier. In fact, but for to visualize, to see the buildings, I mean, to see if there's anything going wrong, it's simple. It's easier to go through the UI, the user interface. I mean, the software. So so that's that's the thing. One more thing, for all the UVM software, what happens is, for example, the scenario which I'm showing here, C users, Arunim Anand, and CA models, this is actually stored here in C users and Arunim Anand. I have created this folder, CA model. Yeah, so demo 1, demo scenario 1. You can see everything is very simple. Input means all those inputs which were there in the model. All inputs are here in form of shapefile. So if someone is familiar with GIS software or anything, they can, these DBF softwares can be opened in Excel. Those SHP format files can be opened in GIS, and for example, these can be opened in GIS as well as Excel. And for example, the schedules for all the buildings, we have different Excel files created here. So the interface is simple, even the input files are simple. And once the output is done, I mean, once we go back to demo scenario, output, data, occupancy. See, for the solar radiation, for all the buildings, we have the file generated here because that job is completed. So you can go and look into each and every data. It is that simple. Okay. So I would like more people to, well, yeah. So this job is done. Energy demand is calculated, and this is the last thing that I'll just show you software. So I will just add a plot. What is the result? Energy demand. Let's say energy. I want to see energy use intensity for all the buildings. I click OK, and it will give you a nice chart of all the buildings where we have end use space cooling demand, water demand, electricity demand. You can bifurcate it as well. There are more options, but for simplicity, I mean, for time being, I've just shown you this graph. For this, because all the buildings were very similar, so the energy demands are very similar to each other. Otherwise, the graphs can be up and down. It can be a sinusoidal curve as well. So yeah, that's it. Stop sharing. Yeah. I hope you liked it, and I hope it was simple to understand.
Yes, no, thank you so much, Arnim. So I'm just looking at the comments in the chat. So there's a comment from Bath. I would like to appreciate Engineer Anand for his presentation despite the disturbances he experienced. Thank you for the extra effort. And then there's another comment from
Gaurav Ganji. Oh yeah.
Yes. Just to give her thanks as well. And also a very insightful presentation. There's also a question from Q. I just don't see the full name. He's asking, How can someone get the presented paper, and is there a certificate?
Yeah. So
Uh,
the work that I have shown in my slides is some of the work has been published in a journal, and some of the work has been published as a conference paper. So I'll probably share the link with either Fortune or someone, the DOI of of the the paper. And one of the work is still under review. I mean, not under review. I mean, we have created a draft, but it has to go through a peer review and then it will be published. So it will take some time. But for some of the papers, I'll share the DOI with Fortune, okay? And you can access it easily. It's I think it's open access online.
Thank you so much. Thank you. There's also a comment from Womu Timi. Yeah, he's also thanking you for insightful presentation. Are there any other questions? Anyone would like to raise any other questions before we close? Okay, I don't see any hands. On my side, I do have a question. I'm a little curious because this really is a very interesting topic, your research on UBEM. So I would also just want to find out when it comes to zoning, can this actually alter existing zones when you use when using the UBEM to determine the energy demand in certain areas of the city for maybe future projects, for new projects? 'Cause you did mention that there's a 70% new energy consumption. I think maybe this data, this percentage is only specific in India, or is it worldwide for new uh, buildings? Because when there's
Okay.
new buildings, there's new energy consumption. So does that alter now when it comes to zoning, when we now add new buildings, that now changes?
Okay. I would say very interesting question. In fact, I would like someone to work upon this because absolutely there is an answer. I mean, the answer is yes. So the thing is, uh, the buildings that we created here for the demonstration were existing buildings, right? I mean, they were existing in the campus already. But if you want to if you want to create a zone of an area which is going to be developed in future. I mean, let's say you have a master plan or something like that of an upcoming project defined by your government or your municipality, that in one particular area someone is trying to set up uh, a colony or a what is that? I mean, technological park or anything. If is there any upcoming project, you can create all those shape files, I mean the buildings which I created, and you can import it directly in any UVM software. Not even in not only in City Energy Analyst, but in any of the other UVM softwares as well. You just have to create the you can use the CAD drawing, the CAD drawing that we use in civil engineering. You can use that CAD drawing. You can just georeference it, which means that you will just use that CAD drawing for that particular area. I mean, let's say, I'll give you an example of my city. If I know that there is a project coming up in Mumbai, in the outskirts of Mumbai, where they are going to develop a small city or a satellite town with 1,000 buildings, I can take their plan. I can create those buildings by my hand or even by any open source GIS software, and I can use that in a shapefile format and import in this model, use a future climate data set, and can predict the energy demand. Right. So basically, that is actually somewhat it is very much related to my research objective in PhD, where I'm not trying to take the plan from somebody. In fact, I'm trying to give an optimum solution for an efficient city, a sustainable city. So what can be the orientation, what can be the compactness of an urban area of number of buildings which can be built in a way that the energy demand is optimized. So that's what I am working on, and it's very interesting, and anyone can take it up, definitely.
Oh, thank you so much. Yeah, thank you for answering my question. There's also another comment that just came in the chat. This is more of a note from Fortune saying that please drop your emails for further communication, including certificates. Okay, so thank you, everyone. We have now reached the end of today's webinar. Thank you all for joining today's webinar, and we look forward to seeing you in the next month's webinar. Before we close, are there any announcements? Mr. Fortune, are there any announcements?
No, not at all. Please go ahead.
Okay, thank you. Thank you so much. So there will be a memo or a newsletter that will be circulated to everyone regarding next month's webinar, all the information regarding next month's webinar. So once again, thank you, everyone, and a special thanks to our guest speaker, Arunem Anand. And please feel better soon with your cold.
Yeah.
And have
Thank you very much.
yes.
Thank you. Thank you,
And,
everyone. Thank you, everyone, for joining. Thank you, everyone.
have a wonderful day, everyone. Thank you so much. Bye.
Bye.